What's up, you guys? Today we're watching PBS talking about sterile neutrinos, and I'm going to try to see how it fits into my hypothesis. Let's get into it.
On to the episode. 3 generations of quarks and leptons, with each generation bisected via isospin. For the leptons, that splitting gives us the massive electrons, muons and taus, and their corresponding ultralight neutrino counterparts. That's the simplest representation of the standard model, but all of these are split again into matter and antimatter, and there's one more less.
So I think that antimatter is actually part of the power dimension, which they aren't real particles, but rather the source of where particles come from, kind of connecting the fermions that we know to the power dimension, which is where they come from.
Lesser known reflection, chirality. This is a sort of fundamental handedness or spin relative to the direction of motion. Left and right-handed quarks, left and right-handed electrons, muons and taus. But weirdly, here, cosmic symmetry seems to fail. There are only left-handed neutrinos. No right-handed neutrino has ever been detected, which seems odd at first, but may not be so surprising. Regular left-handed neutrinos are famously very difficult to detect because they only interact via gravity and the weak nuclear force, both of which are notably weak. The weak force being 10 to the 24.
So I kind of think that the reason why there's no right chirality, the reason why chirality exists, the reason why there's no right-handed neutrinos, one, I associate neutrinos with the zero dimension, and also Z bosons, but I'm thinking maybe that is evidence of the fact that power flows from the power dimension directionally angulared into the dimensions. Starts with power dimension, and so I invented these things called angulars, and they're basically what sort of defines our orientation, them with axions as well, creating the ratio that we get, that results also in the inverse square effect or whatever. But anyway, let's keep going.
4 times stronger than gravity is the only way that we can actually see individual neutrinos. However, the weak force is also victim to the broken cosmic symmetries. It only affects particles with left-handed chirality. Right-handed particles simply don't feel it. So, lacking any other type of charge, the right-handed neutrino has no way to interact with any of the forces of nature besides through its negligible gravity.
Now, what I'm thinking though is, of course, once you get past zero, why do we have chirality, in all the other fermions, electrons? I think electrons are the first dimension, down quarks, the second dimension, up quarks, the third dimension, the fermions anyway. And I think it's because all of those have the ability to decay into neutrinos. Now, neutrinos don't have an ability to decay. Anyway, let's keep going.
Gravity. And this is why we call this hypothetical particle the sterile neutrino. It is barren of any capacity for interaction by the quantum forces. If regular neutrinos are difficult to detect, sterile ones seem to be impossible. So, these gaps in the standard model are missing because perhaps we haven't detected the particle. But there are some major problems in physics that could be solved very neatly if sterile neutrinos do exist. It's for this reason that physicists have been hunting for the sterile neutrino for decades, and why they were getting excited as subtle evidence of.
Again, okay, it's really early to be saying all my theories right now, my hypothesis in development. But I don't think you need a sterile neutrino. In my framework, you don't need the sterile neutrino, and you're not going to find it. Well, let's keep going.
The sterile neutrino started to grow, And it's for this reason that the brand new results from the Fermilab microboon experiment are so shocking. Our most advanced experiment yet suggests that this hole in the standard model really is empty and that the sterile neutrino doesn't exist at all. Let's start with why the right-handed neutrino was really left out of the standard model in the first place. When Weinberg, Salam and Glashow put the finishing touches on the standard model, they were as economical as possible. They only included particles needed to explain our observations. The chiral reflections of the quarks and the heavy leptons were non-negotiable, largely because these are needed to give these families of particles mass by granting a connection to the Higgs field. But
saving money feels right. Just like when things are packed tidy and tight. Get auto insurance that fits your budget and your needs. Save up to 10% when you bundle auto and renter's insurance.
in the 1960s, we didn't know whether the neutrino had any mass. In fact, Weinberg et al. Assumed that it did not. Not only was the right-handed neutrino not needed, but including them generated problems with certain conservation laws, lepton flavor to be precise. Cleaner to just leave them out. It wasn't until the 1990s that we discovered that neutrinos do have mass after all. We discovered that neutrinos spontaneously oscillate between their three flavors, electron, muon, and tau. That can only be true if they have mass, and as it turns out, it's an absurdly tiny mass. We don't know how neutrinos get their masses, but we just eliminated one of the main reasons that Weinberg et al. Left out sterile neutrinos from the standard model. They could, in principle, do the same job as the chiral reflections of electrons, granting mass via the Higgs mechanism. In fact, they can solve two mysteries at once. The extraordinarily tiny mass of the neutrino warrants its own explanation. If sterile neutrinos exist, and if they're actually extremely massive, then they could A, explain why neutrinos have mass, and B, drive down the mass of regular neutrinos through something called the seesaw process, not something to get into today. There's another use of a hypothetical particle that's both massive and impossible to detect by any means other than gravity. That's the exact requirement for the elusive dark matter particle. So, sterile neutrinos seem tailor-made to explain why 80% of the matter in the universe is invisible. And so, the search for the sterile neutrino began. But how do we go about detecting the undetectable? Regular neutrinos are hard enough. They only interact via the weak force, and the weak force has a very short range. That means a neutrino has to pass very close to an atomic nucleus for anything to happen. For a mid-energy solar neutrino passing through the Earth, there's only around a 1 in a billion chance that it'll be stopped by a nucleus. But when that does happen, its energy gets converted into a cascade of particles that, in principle, can be seen. So we can see neutrinos as long as we play the numbers right, enough neutrinos through a big enough detector. But what about sterile neutrinos? If they don't interact by the weak force, what hope do we have? Well, a sterile neutrino can't exchange force-carrying bosons with other particles, but it
I
can
also view the weak force as zero-dimensional, just to say that.
interact with itself in a certain sense. In particular, it can participate in the neutrino oscillations that I mentioned earlier. If electron, muon, and tau neutrinos can transform into each other, then they can also transform into their chiral reflected counterparts, the sterile neutrino. And this is where we have a prospect for detecting them, by looking for anomalies in the oscillations of known neutrino flavors. Let's look at the first effort to catch the sterile neutrino as an example. This was at Los Alamos in the 90s with the liquid scintillator neutrino detector. This experiment goes like this. A beam of muon neutrinos from a particle accelerator is directed into a vat of mineral oil. When a tiny fraction of those neutrinos collide with a neutron, one possible reaction is for the neutron and muon neutrino to be converted into a proton and a muon. The muon zips off through the oil at near the vacuum speed of light. In fact, the muon is moving faster than the diminished speed of actual light in that oil. This leads to something like an optical sonic boom, what we call Cherenkov radiation, and it's that radiation that LSND detected. A similar reaction can happen if the incoming particle is an electron neutrino instead of a muon neutrino. In that case, it produces a proton and an electron rather than a muon. That electron will still produce Cherenkov radiation, but because that electron is much lighter than the muon, it decelerates quickly, and in the process it emits other photons, which themselves can undergo pair production to become electron-positron pairs, which emit further Cherenkov photons, which induce further pair production, etc., with the process continuing until the energy dissipates. This is called an electromagnetic cascade. The Cherenkov ring produced by the electron and the messy EM cascade is fuzzier and fainter than the crisp, bright ring produced by a muon. This is what allows scientists to distinguish.
So I also kind of think that that's why we have the ability to distinguish something that we call now, right? Because if chirality, just think about it, is almost if you have the sterile neutrino, what's the difference between chirality and parity, really?
Distinguish whether the incoming neutrino was of the muon or electron flavor. Even though the LSND experiment used a muon neutrino beam, there are two ways for it to see events from electron neutrinos.
The Bronco encourages us to be a little bit more adventurous.
It makes us find a reason to get out of the house.
One is that there's a very small contamination of electroneutrinos in the beam and from cosmic rays and things like that. The other is that muon neutrinos can oscillate into electron neutrinos before reaching the tank. However, the LSND experiment was set up so that the detector chamber was way too close to the beam source for the oscillations to occur in significant numbers. Basically, it expected very few electron neutrinos, and that design is the key to finding our hypothetical neutrino type, the sterile neutrino. If the sterile neutrino exists and has a relatively low mass, it gives the muon neutrino an intermediate step to oscillate into an electron neutrino. That massively increases the chance of that transition, enabling a good number of muon neutrinos to flip before reaching the LSND chamber. The
Which doesn't
outcome
happen.
should be that LSND saw many more electron-induced electromagnetic cascades. And it saw exactly that. Enough to point to sterile neutrinos with a mass of around 1 electron volt, which puts them at the low end of possible masses. This was compelling enough to inspire follow-ups. The mini-boon experiment at Fermilab, built in the 2000s, was designed to test the emerging anomaly with higher sensitivity, more neutrinos, a bigger tank of mineral oil, etc. In 2018, Mini-Boon released its final data, and once again they saw an excess of fuzzy Cherenkov rings consistent with electron-muon events, and supporting the 1 EV sterile muon hypothesis. Another very different type of experiment also supported this. The Italian Galax and the Soviet SAGE experiments looked for conversion of gallium into germanium after impact with electron neutrinos. Too few conversions were observed in both experiments, and one explanation was that these electron neutrinos were depleted by converting into sterile neutrinos. The interesting thing here is that the sterile neutrino would also have to have a mass of around 1 electron volt. This feels like it's coming together in support of the sterile neutrino, but there are two reasons not to colour in the gaps of our standard model table just yet. The first is that there are contradictions to the sterile neutrino hypothesis. Other experiments similar in design to LSND and Mini-Boon found no excess of electron neutrinos, and several experiments found another contradiction. If muon neutrinos are converting into sterile neutrinos, there should be fewer muon neutrinos. But that's never been detected. not from accelerator experiments, not from nuclear reactors, and even the neutrons from the Sun, as measured by the Ice Cube Observatory at the South Pole, are perfectly consistent with neutrinos oscillating only between the 3 known types. So we have these different types of
Another thing that I think that would prove that, that it would make sense with is the inverse square law, as far as my theory with neutrinos, my hypothesis developing with neutrinos being the zero dimension. The thing is, we don't need that because there is the power dimension, right? So there's no need for, literally, what would be weaker than the zero dimension? What would be the internal whatever, inverse square law. I can't get any smaller than zero. Zero with mass, with tiny mass. So
experiment giving weirdly contradictory results. Finding sterile neutrinos would be incredibly important, but it's also important to figure out this discrepancy. Mini-Boon needed to be upgraded to Micro-Boon, that's short for Micro Booster Neutrino Experiment. It was designed to eliminate the main source of uncertainty in its predecessors. So one way to explain the electron excess in both Mini-Boon and LSND was that these fuzzy electron Cherenkov rings may be due to something completely different. Neutrino collisions often produce neutral pion particles, which then decay into pairs of gamma rays, and those in turn can create electron-positron pairs via this pair production. And those particles can then produce their own cones of Cherenkov radiation and electromagnetic showers. If those showers happen to overlap, the resulting ring can look just like the single rings from a proper electron-neutrino event. Micro-Boon's main job was to filter out these false signals. We'll call them photon events from the actual electron-neutrino events. Micro-Boon sits downstream of Mini-Boon on the same neutron beam at Fermilab, but it's built around a completely different technology, a liquid argon time projection chamber. Mini-Boon distinguished between muon-like or electron-like events based on the quality of the Cherenkov rings, but this new chamber type can actually track the detailed trajectory of the particles produced in the neutrino collision. This gives a foolproof way of sorting real electron-neutrino events from the false ones that I described. So when a neutrino hits an atomic nucleus, there's always a spray of various charged particles like protons and pions from the point of impact, the vertex. That allows us to localize the collision point. If a muon is produced by a muon neutrino, its track will begin at the vertex and it'll travel a long distance in a straightish line. If an electron is produced by an electron neutrino event, it'll travel a shorter distance and then create an electromagnetic shower like I described. Remember that with Mini-Boon, these electron events were hard to separate from photon events. In the latter case, we have a neutrino impact and the resulting spray of particles, which includes 2 gamma ray photons. These then travel through the tank, leaving no track at all until they themselves convert into electron-positron pairs, which then start a visible electromagnetic cascade.
Scribe is how you stop explaining the same thing over and over at work. Watch this. It'll change your life.
So the way to distinguish a genuine electron-neutrino event from one of these false events is that there's a clear gap between the collision vertex and the beginning of the EM.
Also, in my hypothesis, the gap would exist really maybe on the order of like seconds, but maybe the gap itself is the space between electrons being one-dimensional in my hypothesis, photons being third-dimensional. You have to step up that resolution governed by what I call angulars, which are sort of partners of axions, if we want to get into that, but would take some time in order to transition between the one-dimensional and three-dimensional.
Cascade. So, what did Microboon find? Well, not the sterile neutrino. It found no excess of electron-neutrino events that might indicate a sterile neutrino in the mix, once Microboon eliminated the false signal from the photon events. The first Microboon data release and results were published in 2021, and already it was not looking good for the sterile neutrino. And at the end of last year, December 2025, the Microboon collaboration published new results in which a source of confusion was removed using a second neutrino beam. The absence of an electron neutrino excess was confirmed. This final analysis was also able to confirm that the apparent excess observed by Mini-Boon can be completely accounted for by photon events, and it ruled out sterile neutrinos as the cause of the anomaly in the early gallium experiments. So why is this a big deal? Well, the sterile neutrino is probably the simplest possible extension of the standard model, and so the anomalies observed in earlier experiments made its existence feel very plausible. Microboon has basically eliminated...
In other words, they were trying to complete the symmetry, but with missing parts.
any of the evidence for the sterile neutrino. That sends the particle back into the realm of pure speculation. We have no empirical evidence whatsoever to believe it exists. But it may still exist. Microboon is sensitive to a mass range of around 0.1 to 10 electron volts, but if the sterile neutrino has a much higher mass, it could still be out there. And that means that the particle remains a solid prospect for explaining the tininess of the other neutrino masses and for the existence of dark matter. For those, the sterile neutrino would need to be...
So if it does exist, it's almost like a quasi-neutrino, really, a larger layering of neutrinos.
many orders of magnitude larger than the sensitivity of Microboon. In fact, the non-existence of light sterile neutrinos could even be seen as a boost for this particle's role in those mysteries. But to detect massive sterile neutrinos, we need to try other things. And there are various works in progress to look for the subtle signatures of their existence, both in labs and out there in the universe. And these are topics for another time. But in the meantime, our congratulations to the good folk at Fermilab for sorting out this strange anomaly and for their continuing effort in understanding the neutrino,
Shout
the
out to
most mysterious
Fermilab.
particle in the standard model. And if you want to learn more about their neutrino program, maybe watch that episode when Don Lincoln and Fermilab actually hosted PBS Spacetime. Thank you to Bubble for supporting PBS.
So that was that. I hope you enjoyed it. Go ahead and like and subscribe, and we'll get into more fascinating stuff. It's really cool, really cool episode.